German railway engineers faced a strange problem. Locomotive boilers were exploding without warning. Investigators blamed pressure valves and metal fatigue. But the explosions kept happening anyway. Nothing unusual appeared inside the wreckage. Because the weapon never looked like a weapon. It arrived hidden among ordinary coal, a single lump placed quietly inside the fuel pile. Sooner or later, a worker shoveled it, and the furnace finished the sabotage. A German locomotive exploded during routine departure. The boiler tore open under sudden pressure. Maintenance crews searched immediately for mechanical faults. Engineers examined shattered boiler plates carefully. Investigators blamed fatigue within aging metal structures. Another locomotive exploded days later under similar conditions. Then another engine failed inside a rail depot. German rail authorities noticed a troubling pattern. Boiler explosions appeared without warning or explanation. Inspection teams searched for design weaknesses. Nothing unusual appeared within damaged engines. The cause rarely remained inside the wreckage because the explosive had already burned away. It arrived hidden inside ordinary coal fuel. British planners had studied German fuel dependence carefully. Railways relied entirely upon coal-powered locomotives. Factories depended upon coal-fired industrial boilers. Electrical stations burned coal to produce power. Coal therefore moved constantly through transport networks. Rail yards stored mountains of fuel beside tracks. Workers shoveled coal continuously into locomotive tenders. Fuel passed directly from depot piles into furnaces. Coal fragments rarely received careful inspection. The British sabotage planners recognized the vulnerability immediately. Direct attacks against railways risked agent exposure. Explosives near depots triggered instant suspicion. Sabotage required a device requiring minimal contact time. The device also required natural concealment. Coal itself offered the perfect disguise. British Special Operations executive engineers developed the concept. The plan required explosive disguised as ordinary coal. The device became known as the Coal Torpedo. Engineers began collecting authentic coal fragments. Coal pieces displayed irregular shapes and sharp fractures. No two fragments appeared identical in structure. Any imitation required convincing natural surface patterns. Engineers examined coal from multiple British mines. They recorded size ranges used by locomotives. Typical furnace coal measured roughly 10 centimeters wide. Weight also required accurate duplication. A lighter fragment might attract suspicion. Engineers therefore copied both mass and appearance. Real coal samples provided molds for casting shells. Molds captured natural cracks and broken edges. Coal dust became the primary shell material. Powdered coal mixed with industrial binding resin. The mixture hardened into dense black structures. Surface coloration matched genuine coal precisely. After casting, workers modified shell edges manually. Tools chipped fractures across shell surfaces. Technicians rubbed shells against real coal piles. Abrasion removed any unnatural casting smoothness. The finished shells appeared indistinguishable from coal. Shell interiors contained cavities for explosive cores. Engineers selected Nobel 808 plastic explosive. Plastic explosive allowed shaping within irregular cavities. The material remained stable during transport. Each coal torpedo carried roughly 400 grams explosive. Confined boilers amplified explosive pressure dramatically. Detonators were embedded inside explosive blocks. Each detonator connected to a thermal ignition system. The device remained inactive until furnace temperatures rose. Coal fires exceeded 200 degrees Celsius easily. Once inside the furnace, ignition became inevitable. Thermal compounds burned through a short delay mixture. Seconds later, the detonator activated. The explosive charge then detonated instantly. This detonation occurred inside pressurized boilers. Boilers already contained heated water under pressure. Water converted rapidly into expanding steam. But the explosive shock disrupted pressure equilibrium immediately. Shockwaves struck furnace walls with violent force. Boiler plates absorbed sudden pressure spikes. Steam reacted explosively inside metal chambers. Many boilers ruptured under the internal blast. Locomotive engines sometimes suffered total destruction. Even moderate damage removed locomotives from service. Repairs required specialized railway engineering workshops. Damaged locomotives occasionally blocked rail lines. Clearing wreckage delayed transport schedules further. Factories also depended upon coal-fired boilers. Coal torpedoes entered industrial furnaces as well. Explosive detonations shattered furnace interiors violently. Steam pipes burst across machinery halls. Production lines stopped during emergency shutdowns. Repair crews dismantled boilers for inspection. German engineers frequently blamed mechanical malfunction. Boilers sometimes exploded from internal pressure failures. Coal occasionally contained trapped gas pockets. These explanations appeared plausible to investigators. Coal combustion produced soot-covering blast residues. Forensic evidence remained difficult identifying clearly. This confusion protected the sabotage operation. Coal torpedo deployment required minimal agent exposure. Resistance operatives targeted unguarded coal depots. Coal yards existed beside railway facilities everywhere. Massive piles of black fuel waited beside tracks. Workers shoveled coal rapidly into locomotive tenders. Agents required only seconds near the piles. Devices slipped quietly among thousands of fragments. Once mixed, the device disappeared completely. Sooner or later, workers shoveled the device. Yet the disguised explosive entered locomotive furnaces. Moments later, ignition began within the firebox. Then, the boiler explosion followed unexpectedly. Railway maintenance teams rushed to damaged locomotives. Inspection crews examined ruptured boilers carefully. Reports described sudden, unexplained internal blasts. Mechanical failure remained the official explanation. Coal torpedo sabotage therefore continued undetected. SOE workshops produced the devices carefully. Manufacturing occurred in small, controlled batches. Security procedures limited knowledge among workers. Shell fabrication teams handled coal dust casting. Explosive technicians prepared plastic charges separately. Detonator installation occurred during final assembly. Safety officers supervised explosive handling procedures. Finished devices passed weight verification tests. Technicians compared shells against genuine coal samples. Defective units were dismantled under safety protocols. Approved devices were packed among real coal pieces. Transport crates resembled ordinary fuel containers. Distribution moved through clandestine supply networks. Aircraft dropped sabotage equipment into occupied Europe. Resistance networks retrieved supply containers secretly. Local cells distributed devices across railway regions. Rail transport remained essential for German logistics. Troop movement relied heavily upon rail networks. Coal torpedo sabotage therefore targeted critical infrastructure indirectly. Destroyed locomotives forced immediate equipment replacement. Repair workshops filled with damaged engines. Spare locomotive availability gradually decreased. Rail schedules required constant adjustment afterward. Railway officials struggled explaining repeated explosions. Security patrols occasionally inspected coal depots. However, detailed inspection proved impractical operationally. Coal piles contained thousands of irregular fragments. Fuel demand required rapid loading procedures. Time pressure prevented individual coal examination. Disguised sabotage devices therefore remained effective. Coal torpedo design required minimal mechanical complexity. Absence of timers improved operational reliability. Thermal ignition relied upon predictable furnace heat. Simple design accelerated wartime manufacturing. Coal dust shells required inexpensive materials. Plastic explosive charges used moderate quantities. Total production cost remained relatively low. SOE therefore continued production throughout the war. But coal torpedo remained one element within sabotage operations. Other devices targeted vehicles, bridges, and pipelines. Yet fuel sabotage exploited constant industrial dependency. Coal powered locomotives across occupied territories daily. That dependence created unavoidable vulnerability. The coal torpedo exploited that vulnerability precisely.